All right, let's talk about relativity. I know, it has this reputation for being incredibly complicated. But what if I told you that's not really true? Today, we're going to throw out the old, confusing rulebook and use a new, much simpler way to make it all just click.
So let's kick things off with a little mystery. You're in your car, you look down at the speedometer. It's telling you your speed. Easy, right? But think about it. What is speed? It's distance divided by time. But whose time? Is it measuring against some clock on the side of the road, or is it using the clock inside your car? Just hang on to that question for a minute.
And here's puzzle number 2. Your phone has this little chip inside, an accelerometer, that feels every push, pull, and shake. But what happens if you drop it? For that split second it's in free fall, the accelerometer's reading goes to 0. It suddenly can't feel the one force that's yanking it toward the ground. How is that possible?
Well, the answer to both of these puzzles comes down to looking at spacetime in a totally new way.
So why does learning relativity usually feel like running full speed into a brick wall? Honestly, it's the way it's taught. The traditional approach can be super confusing and, frankly, just doesn't feel right.
You see, the standard way forces you to constantly jump between different points of view. One minute you're here, the next you're over there. And you get tangled up in these bizarre-sounding ideas like length contraction, where things supposedly shrink when they move fast. It's a mess, and it makes something beautiful feel really, really awkward.
But there is a much better way. The aha moment comes when we make one simple change. We're going to stop jumping around. We'll stick to a single map of space. But, and this is the key, we're going to use 2 different kinds of time. We're going to adopt the traveler's point of view.
Okay, so clock number 1 is what we'll call map time. Think of it like this. Imagine there's a whole network of perfectly synchronized clocks, maybe one at every mile marker along a highway. Map time is the time that they measure as you whiz past. It's the official timekeeper of the world you're moving through.
And then there's clock number 2, traveler time. This one's easy. It's the watch on your wrist. It's the clock in your car's dashboard. It's the time that you, the traveler, are actually experiencing. This is your personal time. And here is the absolute heart of relativity. These 2 times are not the same. They don't tick at the same rate. The faster you move through space, the slower your traveler time ticks compared to the map time. It's a fundamental trade-off. So how do we link them? With this one single equation. I know it looks a little scary with the squares and the letters, but trust me, this is it. This is the master key. It's the only rule you need to connect the time on your watch to the time on the map, based on how far you've gone. And the coolest part? This isn't some scary new math. It's basically Pythagoras' theorem. You know, a squared plus b squared equals c squared, but for space-time. In geometry, the long side of a triangle, the hypotenuse, has a fixed length. In relativity, your traveler time is kind of like that. It's this fixed, unchanging thing that everyone can agree on.
All right, so now we've got our simple toolkit. 1 map, 2 clocks, and 1 rule. Let's go back and crack those puzzles wide open. So that speedometer, what's it really measuring? It's measuring the distance you've covered on the map, yes, but it divides it by the time that's passed on your clock, the traveler's clock. This is called your proper velocity, and it's a measure of how fast your personal clock is aging relative to the distance you're covering. And the phone. Okay, so when you're just holding it, it feels the force of your hand pushing up. Makes sense. But the second you let go, it's in free fall. Gravity is pulling on every single atom of the phone in exactly the same way, so there's no internal stress, nothing to push or pull against. It feels nothing. Then, when it's caught, bam, a huge spike of force. And that tells us something profound. The accelerometer can only feel what we call proper forces, actual physical pushes and pulls, like being caught. It is completely blind to geometric forces, like gravity, because gravity isn't a force in the way we usually think of it. It's the shape of space-time itself. And when you're in free fall, you're just following that shape. This whole approach just makes everything cleaner. You look at the standard textbook formulas for things like momentum or energy, and they're a mess. But when you rewrite them using traveler time, they suddenly become simple
elegant and look a lot more like the clean formulas we all learned in high school physics.
Now, this isn't just a neat trick for solving little puzzles. This way of thinking scales up big time. It lets us get a handle on some of the most extreme events in the entire universe.
Let's head over to the Large Hadron Collider. We're taking protons and accelerating them to insane speeds, then smashing them into each other. You can try to calculate the energy of that collision the old way, but if you look at it from the proton's point of view, from the traveler's perspective, you get a much more real, a much more visceral sense of the incredible power being unleashed. So just how much more powerful is it to smash two protons together versus firing one at a stationary target? It's a huge advantage. We are talking almost 14,000 times more bang for your buck. That number right there is why we build colliders.
Okay, time for some sci-fi that's actually not fiction. Let's imagine we build a spaceship that can accelerate at a constant 1g, a nice, comfortable gravity like we have on Earth. Figuring out that journey with standard relativity is a total headache, but with our Traveler Point toolkit, it's surprisingly simple.
And the results are just wild. If you were on that ship, after just 5 years have passed for you, 28 years would have gone by back on Earth. You travel for 10 years, that's 840 years back home. And if you keep going for 15 years on your personal clock, a mind-blowing 25,000 years will have passed on Earth. You'd come back to a completely different world.
So there you have it. We took this big, scary topic and made it feel natural just by changing our perspective. Let's just quickly wrap up the rules for this space-time smart way of thinking.
Here are the 3 simple rules. 1, always ask, are we using the map's clock or the traveler's clock? 2, to keep things from getting confusing, just stick to one map. Don't jump around. And 3, remember the difference between forces you can feel, the proper forces, and forces you can't, like the geometric force of gravity.
Which brings us to a final thought. Really, this whole thing was about the power of finding the right point of view. We made one of the toughest subjects in physics feel intuitive just by looking at it differently. So it kind of makes you wonder, right? What other big, complicated problems out there are just waiting for us to find a new perspective and suddenly become simple?